It's like in a presenter view. No, no.
Yeah. Can you see the screen where right now? Can you see
I can see
the
it. Yeah.
presentation mode or? Okay, got it. So yeah, thank you for having me today. So my name is Manho Park, and today I'm going to talk about CNN-based surrogate advection model emulating finite volume method. So basic idea is using convolutional neural network, predicting the flux term, which is in the one of the important feature in the finite volume method, and then use it to air quality model like this. So eventually we can get cool advection result. Before beginning this talk, I would like to acknowledge this work was made possible thanks to all my research group and also my mentor like Chris and Nicole, Zhonghua. And those are some of my community, like student community at UIUC. I basically check like demographic in Slack community host. Seems like people are studying at LA or Boston, like cool cities. But if you are studying at very, very Midwestern campus town, the students are the best thing you can enjoy, like because they are nothing. So anyway, they are basically mental support to me. I always appreciate to them and the funding agencies. And I also want to say this work was also possible thanks to an email from Ovin, because he suggested me to use block-based network, which can conserve the mass. So I'm going to talk about that a little bit. So let me begin the presentation right now. So now we all know transport matters in air quality, probably thanks to the wildfire smoke during the last summer. Now the wildfire smoke problem is not only in the Canada or California, but it can travel across New York City or Chicago, wherever. I mean, this is good thing for us probably because we can get a job, we can secure a job thanks to wildfire. But anyway, this is the certain problem we need to tackle. And the reason of like overall outreach is because of transport. So Champaign-Urbana is 2-hour drive from Chicago. It's not much like Chicago, but in the wildfire day, I could clearly see the difference in the visibility during the wildfire day and not in the wildfire days. So this is quite big problem right now. So if you have a good transport model, then we can resolve that issues. We can do some like computational experiment, what solution will be effective to mitigate, or we can predict when or where it will travel. But transport model is quite expensive. In the chemical transport model, like geochem or whatever, usually the first most expensive things are chemistry model. So like Macro was working on that project. And transport is the second most expensive. And the reason is we need to solve the mass balance equation in multiple boxes of grid cells. So we discretize the Earth system into the multiple grid boxes and then solve the mass balance equation within one grid cells. And to have a great result, we need to run the simulation with a high resolution, which will take a long time because we need to solve much more number of simulation. Rather, maybe we can say we can use smaller size, low resolution representation. But in that case, the computational error or numerical diffusion will be high. So it's always the traditional dilemma, whether you will choose accuracy or speed of the simulation. And our group's philosophy is data-driven method can tackle that traditional dilemma because the data-driven model can be accurate and also low resolution somehow. So the idea is first we can run high resolution simulation using the existing model and then regrid the output to the low resolution. And if we use that output to train the model, then the machine learning model output will be accurate because that training data set was from high resolution data. But the dimensionality will be way lower than the original data set because anyway, we make it into the low resolution. So that is idea to reduce the computational cost and keeping the accuracy. So maybe in this community, no one will ask me like why faster model is good, but I have some of friend who is working on experiment, who is not working on like modeling. They always ask me, so what? So what is good thing if you have fast model? And it's because I think it's good because the fast model is not only for model simulation, but also it can accelerate the development of science. Let's say the scientific development in like air quality or all system model is first always begin with like model parameter estimation from the observation. And what we do is numerically implement that parameters inside the computer model. And to see if that implementation is correct or not, we need to run the simulation and then evaluate the model output. And then they'll have feedback processes to see if it was correct, or if not, we need to revise it. But what if the model simulation take 2 weeks or 1 month or like very long time? Then it's not easy to fix the problem. And sometimes it's very, very painful. Like think about you have the simulation after 2 weeks of long waiting, and then the result is just blow away, and you don't know where to start, like what to fix. But if the simulation is shorter than that, then maybe we can do better job because it's not too painful. So that is the idea. And this one is my first approach to develop learned advection scheme. So basically, advection scheme is calculating the next time step concentration using like flux operation with DTDX, like first order accuracy, and flux itself also has DTDX information. So it can be like second order accuracy model. And those flux can be defined by 3 stencil points. So I designed my neural net solver to have to replace the coefficient in the numerical model using the convolutional neural network. So here CNN is giving the output as coefficient of the reference like numerical model, which is giving first order and second order accuracy and replacing the 3 stencil point coefficients. So my approach was using convolutional neural network with GALU activation because GALU was somehow known better than ReLU sometimes if the problem is too stiff. And then I used hypertangent activation because GALU or ReLU has like monotonicity. But we want to have the coefficient can be either positive or negative. So to have both direction, I believe having like hypertangent activation is somehow working. Later, I just realized I can just use identity function, but anyway, let's keep going on. Yeah. And then I apply this 1D advection model to the 2D multiple splitting mechanism, which is used in GeoScan. In that work, I developed my model using 1D domain training data set. So basically, I chose that latitudes because it passes the NASA GMAO office, which is the funding agency. So I want to show something like loyalty or patriarchy to the funding agency. So it's just 10 days long simulation with 5-minute interval. And I use like GeoF, WinData, and use the Pioneer-like scheme, which is used in GeoScan. And then I coupled the solver into one chemical transport model, which is Earthside ML model under the development in my research group. Jialin and Chris is working on that part and with some of the collaborators. If you are curious about this work, I strongly recommend you to stop by this talk at AGU. And I think this work is one of the coolest work in my research group happening right now. So basic idea is having a symbolic equation based air quality model, which means you don't need to implement all the code of Fortran or whatever. You can just put the equation and the Julia package will solve that equation by choosing appropriate numerical method. So anyway, I'm coupling my solver into that chemical transport model. Here are some results. First, I got some acceleration with spatial temporal coarsening. Let me check. So what I found was my model can accelerate the reference over simulation with spatial and temporal coarsening. So coarsening factor is very, very high, like 16 times larger space domain and 64 times in temporal coarsening. And the computational time became like 10 times lower than the original model with the CTM simulation. And in case of standalone run, it was just like 300 times faster than the original model, which is quite promising. But there is an issue, which is like it has quite similar spatial pattern, though it has little higher concentration than original model, which can cause stability issue later. So I'd like to fix that issue later. And I want to see if my model can work with splitting other mechanisms. So currently RSI ML has chemistry and emission deposition, I guess. But here I just placed the emission on this horizontal domain because like coupling chemistry will be much difficult problem for me. So just right now, I want to see if my model can resolve constant emission together with the transport. And again, like spatial pattern looks quite similar. R square was like 0.55, but problem is concentration right now way lower than the original solver. It may be because in the coarse graining, it has somehow like averaged out velocity. So the reason it has high concentration here is there might be some convergent velocity. So somewhere velocity can be zero so that concentration can accumulate. But those kinds of things can be averaged out in the portion domain, not only for the concentration, but also for wind speed. So tricky thing is in the transport modeling, it has stability issues. It has higher concentration than original model. And with coupling the emission, now it has somehow lower concentration than original model, which is problematic at this time. But anyway, the biggest problem of this approach was, what I found was, this can do acceleration only if I apply lots of the large factor of the coarsening. So originally in the native resolution, so basically this table is showing the speed up with the matrices of coarsening factor in time and coarsening factor in space. And in the original scale, my machine learning solver is almost 20 times slower than original model. So to get the acceleration, I need to do like, for example, 4dx, 8dt coarsening to get the acceleration. But problem is people are actually more interested in like not losing spatial details because like, so this idea of spatial coarsening was from fluid dynamic simulation. And for CFD community, losing some spatial detail is okay. But for us, GeoScan, for example, has like highest resolution is 0.25 degree, which is already large actually. So we just realized maybe we need to work more on temporal coarsening, but not doing spatial coarsening. But problem was for the temporal coarsening with the native resolution, always the numerical instability occur. So this approach has certain limitations. But still, it can be promising because spatial temporal coarsening issues can be resolved using other techniques. For example, downscaling atmospheric chemistry simulation with like one of the Sam Silva's work. So from the low resolution representation, like getting to the like truss. So if I use same approach together with this one, then maybe this issue will be overcome. But still, I want to have a solver which can keep spatial resolution without losing any details. So let's work on that direction. And I found this model has limitation because of inherent structure is not suitable to solve instability issues. First, it didn't have any physical restriction to conserve mass because it's only giving just coefficient and there is no relationship between that. And another thing is the coefficient is together with the concentration. So it can scale the concentration or scalar, but it doesn't have any information with the velocity. So if I feed the velocity, which was not exposed during the training process, then the instability can occur. So that might be one of the reasons why there are some numerical instability of the model. But to overcome that model, I thought maybe I can predict flux instead of other coefficients like Obin did in chemistry model. So basically, if we predict flux within the at the edge of the boundary, the good thing is flux outward to one direction. From, for example, flux outward from this cell will be flux inward into the neighbor cell. So overall sum of the flux will be zero. So if we predict flux and if we construct a model with the flux form operator, then it can conserve the mass eventually. So that is the idea of the new solver I'm trying to develop. So here, I'm gonna estimate the flux. And another difference is now I'm using CFR number instead of velocity. CFR is relative amount of the scalar advection within the grid cells. So it already scaled the velocity to the dimensionless parameters. So we don't need to worry too much about like scaling velocity if we use CFR number instead of the velocity. And then I use somehow smaller size of neural net. Previously, I used 32 filters per layer for convolutional neural network. But now I use 10 filters to cut down the computational cost so that it can achieve more computational speed up in the same resolutions. And this idea was, yeah, definitely from Obin's paper, and I really appreciate him. And training data set is 1D advection result in the several latitudes. So it looks like 2D, but you can see advection only happen in like horizontal direction. So I train my model with each lines of the 1D advection result. And that is the preliminary result what I got right now. So far I didn't do any coarsening. So this is in the same resolution, same spatial and temporal resolution. Basically I got that result maybe yesterday or Saturday. So it's quite hot and fresh results. Please enjoy it. So it's quite cool because concentration, like spatial pattern looks quite similar. But problem is it develops somehow unnecessary noise like here. So there should be no any concentration, but somehow it developed noise like concentration, even though there is no effect from original source. So this might be some issues with hyperparameter tuning or whatever. So I'm gonna train my model more. Currently, this model was trained only 10 times, 10 epochs. So I hope more training can solve that problem. Anyway, it didn't achieve computational acceleration yet, but it's more promising, and I'll explain why. So here, computational timing with the Earth-IML simulation is taking like 2 times longer in CNN-based solver. And in case of standard running, it's like 6 times slower than original solver. But it's better than previous one because previous one took like 20 times longer simulation in the native resolution. But now it's only 6 times slower. It means if I apply maybe 5 to 6 times coarsening, then it can achieve computational speed up. So with that regard, it's quite promising. And here is some conclusions and future directions. First, our stencil form solver achieves computational acceleration with spatial temporal coarsening, but it has stability issues and it's not working with like just temporal coarsening. So in this regard, flux form solver is more promising, and I hope this can have much higher speed up eventually. And one idea I would like to use is, so basically I'm working Julia, and there is a Julia package which is called simplechains.jl. And I'm currently using the default package in machine learning tool like flux.jl, which is So this simple chains.jl was developed to accelerate the neural network operation in Julia, and is known to be 5 to 10 times faster than flux.jl. So it means because it's 6 times slower in the native resolution. If I apply simple chains, which is like 5 to 10 times faster than flux, then even it can achieve computational speed up in the native resolution, which is I'm very, very excited right now. And later I'll do temporal coarsening with the flux form solver. Yep. That is all I prepared today. And thank you for listening.
Well, that was super interesting, and looks like you've made a lot of headway since your preprint from just a few months ago. So that's really exciting to see. I have so many questions, but I'm sure there are other questions too. So I'll open up the floor to questions from people.
Can you turn off the recording?
Yeah.